Good morning, students. I am Pradeep Singh Yadav, and this one is the second lecture of your VLSI system design syllabus. In this lecture, we will discuss about hierarchy and regularity. Okay, so let's start our topic. First, what is hierarchy? Hierarchy, we can understand hierarchy by using the term position. Before starting this topic, hierarchy in VLSI system design, first we understand it by using by taking any real-time example. Suppose we consider a educational institute, and in that educational institute there are the various positions, there are the various position of staffs that after combination of these all positions the education is possible. Suppose in any institute the highest hierarchy is president, then vice president, director, principal, technical staff, then HOD, then technical staff, then non-technical staff, then peon. All these positions are combined for making a single goal possible, that is to provide education to the student. Okay. Same as when we consider hierarchy in VLSI system design. So we can understand hierarchy by taking a term position. Hierarchy means hierarchy in a VLSI system design. Hierarchy means design and conquer technique. Now, what is the mean of design and conquer technique? To understand hierarchy in VLSI, we are taking an example. Suppose we are taking a system that is 3 6 9 11. Okay, 3 6 9 11 are the elements of the system. For making this system, first we divide the system into modules, so that we can say this 3 6 and 9 11 are the two modules that we gain when we divide a system into two parts. Okay, now this module is further divided into two parts, such as 6 and 3 individually, and here the 9 11 is split into two submodules, that is 11 and 9 individually. Okay, so we can say this system is first divided into modules, then these modules are further divided into submodules. Okay, so these are the different position. So for making this system, we need to combine this position, we need to combine these modules and submodules. Okay, so why we done this? This is this all done for making for reducing the complexity of the system, for reducing the complexity of VLSI system. Okay, it used for dividing complex design into various modules and submodules for making the design easier. Okay, okay, now this division is done until the complexity of submodules is at an understandable level of details. Okay, means we can divide this submodules into a last category, through which the designer can easily implement it. Okay, so we can talk if we talk this hierarchy procedure in a software program. So we know that the software program is a combination of various small sections. So for making this software program, first we divide the program into smaller and smaller section until we get the subroutine. Okay, so this one is all about the hierarchy in VLSI system. Hierarchy is nothing but a division of any system for making the for making the system easier. Okay, so hierarchy can be there in with all domains. First one is structural domain, second one is physical domain, and the third one is behavioral domain. Now, what is the mean of structural domain? It means if we divide a system on different hierarchy on the basis of its structure, then it is under the category of structural domain. If we divide any VLSI system, on the basis of its physical structure, then the hierarchy is in the type of physical domain. Same as if we divide a system on the basis of behavior of their individual modules, then the hierarchy is in the under the category of behavioral domain. Okay, to understand this hierarchy, we can consider example. Suppose in your reference book there is an example of 16-bit adder. So we all know that how we can implement a 16-bit adder. We know that for implementation of 16-bit adder, first we design 16-bit adder into 4 bits adder. Okay, then again each 4-bit adder designed by using a combination of 4 single bit adder. Okay, so this one is all about a hierarchy. That means by using small elements we can build a system. Okay, so we that means we design a certain hierarchy to reach the goal. Okay, so if we design here a example is given. In that you have to design a 4-bit adder circuitry. Okay, suppose for designing of 4-bit adder, if we design your 4-bit adder circuitry by using the combination of 4 single bit adder, that means you divide its structure. Okay, so you divide its structured, so it is under the category of structural domain. Here what we done here, first 4-bit adder is implemented. 4-bit adder is implemented by using 4 single bit adder. That means 4-bit adder is divided into 4 single bit adder. Then each 4-bit adder is divided into sum and carry blocks. Then each carry and sum blocks is designed with by using logic gates. And how can we design logic gate? For representation or for designing of logic gate, we know that we need to use logic functions, certain boolean logic functions. Okay, so for making the boolean logic function, first we built a logic through which we are moving towards the boolean logic function. Then by using logic gates we implement the that boolean function. Okay, so these are the positions. Suppose this one is the first position, this one is the system, this one is the module, then submodule, then then this one is the again part of submodules. Okay, so these all are the positions: first position, second position, third position, and fourth position. Here this representation is used to represent the each position. Suppose here 4-bit adder is present, so represent this 4-bit adder we use this type of symbol. Here a 3 colon 0 represent represent input representation. This one is the representation that we used in VHDL program. Here a3 colon 0 represent that the input is of 4-bit, that is from a0 to a3. Same as if the second input is also is of 4-bit, then we can represent it by using a3 3 colon 0. Okay, this c4 represent the carry out and the c in represent the input carry. This sum 3 colon 0 represent the sum bit, sum is of 4-bit also. Okay, you know that this 4-bit adder is implemented by using 4 single bit adder. That means each single bit adder need to be designed. So this single bit adder structure is look like the structure that is given here. Here the structure what we here the structure represent that the a is of 1 bit, b is of 1 bit. It means the adder is of 1 bit only. Okay, same same if you represent here what is represented here, represented that there is the sum block and there is the carry block. Okay, so how can we represent this sum block? How can we represent this sum block? This sum block is made by using the logic function, the logic gate, that is AND gate and OR gate. This one is all about represented here. Okay, so this one is the structural domain hierarchy. If we understand the hierarchy on the basis of physical domain, now first of all, what is the physical domain? So suppose we need to design a certain integrated circuit. Then there is some specific space into which we need to combine all the elements. Okay, so suppose this one is the suppose this one is the structure, this one is the IC space. So first we need to need to allocate the space for individual input and output, and by using this input and output, by using this input and output combination, we can implement a 4-bit adder. Okay, so it means to design any integrated circuit, first we need to prepare a floor plan of the circuit. Okay, what is the mean of floor plan? Floor plan means in the integrated circuit where we need to design, or where we need to connect the individual element. Okay, so here a structure of a single bit adder is represented. Here 4 single bit adder is represented, and we connect into the neighbor of their previous one. So the spacing between the two single bit adder is very less. Yes, so that we can easily provide the output of one carry into as an input of another. Okay, so the individual structure of, or we can say individual position of input and output is represented by using this diagram. This one is the representation of physical domain, or we can say the hierarchy of the structure in physical domain. I think from these two domains you can easily understand the hierarchy term. Okay, now the second term is regularity. Okay, now what is the mean of regularity? What is the mean of regularity? In the previous topic, hierarchy, we know that why we prepare hierarchy used to prepare for making the complexity of the circuit easier. Okay, so in that process we divide the circuit into modules and submodules. We divide the circuit into modules and submodules, but in some cases by using the hierarchy topology, we can't minimize the complexity of of the VLSI circuit into beyond the certain limit. So at that time we used a second type of techniques, that is regularity. Now in regularity we divide a system into subsystem, same as that we done in hierarchy side, but here the fixed point is that, but here the certain criteria is that the element, that is the modules and or submodules, the is of similar type. That means for making any system we need to design a similar type of element. This is all about a regularity. It is mentioned here. You can see in this manner of designing, the designer divides the system into similar blocks. Okay, you can consider to understand the regularity term, you can consider the example of memory cell. In the memory cell, the whole memory elements is of same type. Suppose we need to design a 4-bit register. In the 4-bit register, the whole flip flops is of similar type. Okay, so regularity is also divided into a certain level. That is, first one is at circuit level, second one is at logic level, and the third one is at higher level. Now what is circuit level? Circuit level means if we need to design a VLSI circuit, so that at that time first the system is divided into subsystem, and for making the subsystem, if we use a similar type of transistor, that is so that at that time the circuit is in the so that at that time the VLSI system or the regularity is in the circuit level. Okay, now at logic level, suppose we design a circuit, and for representation of circuit we use a boolean function, and by using that boolean function we prepare a combination of various type of logic gates. And if we represent this logic gate structure by using a similar type of gate, then this type of regularity structure is under the category of logic level. Okay, now the third one is at higher level. What is higher level? Higher level means suppose we design a complex circuit. At that time we need to design we need to connect various type of processor. If that processor is of similar type, the structure of that processor is of similar type, then the regularity is in the category of higher level. Okay, now here there are the several features of regularity. What is first one is reuse of design. You can reuse the design if we implemented any circuit by using regularity approach. Second one is simplicity, simplify verification. You can easily simplify the circuit because the whole element is of simple type, so you can easily represent its output part also. Now the third one is construction. Correct by construction, that means if any error occurs, so you can easily correct the error that occur in the system, because the whole element is of similar type, so you can easily understand what happened in the circuit. So here a structure is represented here. This one is the example of regularity. Okay, here you can see, here the system is implemented by using two simple type of element. One is, this one is the tri-state, this one is the tri-state buffer, and this one is the simple inverter. By using tri-state buffer and inverter, you implemented a 2x1 multiplexer here. You know, so if we represent a 2x1 multiplexer by using a similar type of element, then it is under the category of regularity approach. At that time, you can say it is under the category of logic level, because it is using only a two type of structure. You can also implement it by using a simple inverter, or simple by using inverter also, but here inverter and tri-state buffer is used for making the multiplexer circuitry. Okay, here there are the two inputs. First is input 0 and the second one is input 1, and this one is S stands for select. We know that multiplexer is the device that is used for selection of input by using selection line. So which input is transmitted towards the output, it is to be selected by using this selection line only. If we provide this selection line value 1 at that time, if you provide this value 1, then the output of inverter is 0. If the output of inverter is 0, then by using not this, it become 1. So it become 1, but here what happened, if we provide 0, then it become a high impedance level. If it is in high impedance level, that means this input is not transmitted towards the output. But if here 0, then this bubble convert into 1, and this it is into a low impedance stage. At that time we can see the between input and output there are the two buffers. If we connect two buffers in series, then here the two inverter is in series, and we know that if we connect two inverter is in series, then it makes a buffer. So this input 0 is transmitted towards output if we consider this selected value is as 0. Same as in second condition, second value, when we provide the selection line value as 1, then what happen, if we provide 1 as a selection line, then what is the output of buffer? Then here we get 0. Okay, so if we get 0 here, if we get 0 here, so at that time it is in high impedance stage, so this input is not transmitted towards the output. Okay, what happen in if you provide 1, then this one is the low impedance stage. So if this one is the low impedance stage, so it makes a series path here. So in the series path there are the two inverters are connected in series. If two inverters are connected into series, then it makes a buffer circuit. So buffer means the input is equal to output. So we can say if S equals to 1, then this input is transmitted towards output. Okay, so this one is the structure of 2x1 multiplexer by using a regularity approach. You can also consider various type of example. Here the second example is used. Here a register is present. Now what is the mean of register? Register is a memory element. Now what is the use of memory element? Memory element is used for storing any bit. storing the bit of data. Here there are the here this one is the D flip-flop, this one is the D flip-flop, because the input is represented as D, and this one is the clock. So we can easily say that this one is the D flip-flop, this one is the single D flip-flop, and this one is series with again a single D flip-flop. So we can say that two flip-flops make a 2-bit register. Okay, so 2-bit register, here we can say the 2-bit register is implemented by using tri-state buffer and inverter also. So it is also under category of logic level regularity approach. This one is again an example of regularity. You can take various type of example that is represented in your textbook also. So here adder circuitry is present, it is also implemented by using regularity approach. Here the A, B, these are the input that is provided in the adder circuit. The C in is the carry input that is provided to the circuitry, and this sum represent the output of the adder, and this carry represent the carry output of the that we gain from the output side of this adder circuit. Okay, so this one is all about your hierarchy and regularity approach. I hope you understand well. So thank you so much. In next topic we will discuss about modularity and regular and locality approach. Okay, thank you so much.